Welcome to the Sleepy Scientist. It is very good to have you here. Before this quiet little journey begins, it would be lovely to know where in the world you're watching from tonight. Perhaps you're tucked away in bed with the lights low. Perhaps you're on a late train, watching the dark windows turn into mirrors. Or perhaps you're curled up somewhere comfortable, with a warm drink nearby, and absolutely no intention of doing anything productive for the rest of the evening, which is sometimes the most scientifically sensible decision available. Wherever you are, settle in gently. Let the day loosen its grip a little, and if you enjoy these slow journeys through science, a like and subscribe helps this quiet little channel keep drifting along. Tonight's subject is one of those strange ideas that feels completely ordinary until it is looked at too closely. Time is everywhere in daily life. It tells you when to wake, when to sleep, when to wait, when to hurry, and when the kettle has definitely been ignored for too long. It feels as if it flows around everyone in the same steady way, one second after another, calm and dependable, like an invisible river passing through the universe. But physics has not been quite so kind to that simple picture. The more carefully time is measured, the less it behaves like one universal clock. Motion changes it. Gravity changes it. Clocks high above Earth tick differently from clocks down on the ground, and satellites have to correct for it, or ordinary navigation would slowly drift wrong. And then there is the deeper mystery. Most of the laws of physics do not obviously care which way time is pointing, yet life clearly does. Eggs do not unscramble themselves. Smoke does not politely crawl back into a candle flame. Yesterday feels fixed, tomorrow feels open, and the present is somehow always slipping through your fingers before you can properly catch it. If tonight's idea is one you would like to sit with properly, there is now a Sleepy Scientist ebook, Quantum Physics, Explained Clearly. It is written for anyone who wants to understand these ideas slowly and patiently, the way a tricky concept deserves, without the usual panic. It walks through them one careful step at a time, and the full audiobook is included, so you can read it or listen to it in whichever way suits you. The channel runs without ads, so these videos stay calm and uninterrupted, and supporting the ebook is genuinely what keeps this place going. You will find a QR code on screen throughout the video, and the link is waiting quietly in the description. Tonight, the aim is not to make time feel more confusing than it needs to be. Time has already done plenty of that on its own. The aim is to move slowly through what physics can actually say about it, from Newton's absolute clock to Einstein's flexible spacetime, to entropy, black holes, and the real unanswered questions that still sit at the edge of modern theory. So let's begin, shall we? What is time, physically speaking, and why is the universe so much stranger than a ticking clock? Time is so familiar that it can be difficult to notice how strange it is. It is there in the soft passing of an evening, in the cooling of a cup of tea, in the slow brightening of the morning sky, and in the quiet way a room changes when everyone has finally gone to sleep. We speak about time as if it were a thing moving past us, like a river flowing around the edges of life. We save it, lose it, waste it, spend it, and occasionally wonder where on earth it went. But in physics, time is approached a little more carefully. A physicist does not begin by asking what time feels like. That question belongs partly to consciousness, memory, biology, and experience. It is real in its own way, but it is not the simplest place to begin. Physics begins with something quieter and more measurable. It asks what changes, how regularly it changes, and how one changing process can be compared with another. At its most practical level, time is measured through change. A heartbeat can mark time, so can dripping water, swinging pendulums, vibrating crystals, the rotation of Earth, the orbit of the Moon, or the motion of planets against the background stars. Each of these processes gives us a repeating pattern, and from that pattern we can build a clock. The clock does not need to understand time. It only needs to perform some regular physical process again and again. This is the first important idea. A clock is not a magical device that catches a mysterious substance called time and stores it behind a glass face. A clock is a comparison machine. It compares one regular physical process with another physical process we care about. The hands of a mechanical clock move because gears turn. A pendulum clock counts the steady swing of a suspended weight. A quartz watch uses the regular vibration of a quartz crystal when electricity is applied to it. An atomic clock uses the extremely stable behavior of atoms, such as cesium atoms, changing between specific quantum energy states. The deeper the science goes, the more precise the comparison becomes. Long before modern physics, humans learned to read time in the sky. The rising and setting of the sun gave the day. The changing shape of the moon gave the month. The return of seasons gave the year. Ancient sundials used shadows to divide daylight into parts. Water clocks measured the steady flow of liquid from one container to another. In many ancient cultures, timekeeping was tied to astronomy, farming, ritual, navigation, and ordinary survival. Knowing when a river might flood, when winter might come, or when a star would return to the evening sky was practical knowledge written across the heavens in slow motion. This is why time entered science so deeply. To describe motion, we need to know not only where something is, but when it is there. A falling stone, a swinging pendulum, a turning planet, and a beam of light all require time if we want to describe their behavior clearly. Speed is distance compared with time. Acceleration is a change of speed compared with time. Energy, waves, forces, orbits, collisions, signals, and clocks all lean on time in one way or another. Without time, physics would have positions but no motion, causes but no sequence, events but no before and after. It would be like having a beautifully detailed recipe with no order to the instructions. Time also matters because it lets science connect the small and the large. In the human body, electrical signals travel along nerves in fractions of a second. In a quartz watch, a crystal vibrates many thousands of times each second. In an atomic clock, quantum transitions happen with such steadiness that they can define the second itself. At the other extreme, planets take months or years to orbit the sun. Stars can burn for millions or billions of years, and the universe itself has evolved for roughly 13.8 billion years since its early hot, dense state. Across all these scales, time is not measured by one single object. It is measured by regularity. A good clock is a physical system whose behavior repeats in a dependable way. The better the regularity, the better the clock. But this raises a subtle question. If clocks are physical things made of atoms moving through space, sitting in gravitational fields, and affected by the universe around them, then should every clock always agree with every other clock? Is time something outside physics, flowing perfectly while clocks merely try to follow it? Or is time itself revealed only through the behavior of physical systems? For a long period in science, the most powerful answer was that time really did behave like a universal background. It was imagined as steady, absolute, and shared by everyone. Whether a person stood still, walked across a field, sailed on a ship, or watched the moon drift above the horizon, the same cosmic clock was thought to tick underneath all motion. This idea feels natural because it matches ordinary life very well. If two people in the same room compare watches, they expect agreement. If they do not get agreement, they usually suspect the watch, not the nature of reality. The strange thing is that physics eventually discovered situations where the clock is not simply wrong. Under high speeds and strong gravity, time itself does not behave in the simple universal way that ordinary experience suggests. Moving clocks and stationary clocks can record different amounts of elapsed time. Clocks at different heights in a gravitational field can tick at slightly different rates. The difference is usually tiny on Earth, but tiny is not the same as imaginary. With precise instruments, tiny becomes measurable. This is the path that makes time so fascinating. It begins with something humble. change. A shadow moves, a pendulum swings, a planet returns, a crystal vibrates, an atom shifts energy. From these repeating changes, humans build clocks. From clocks, physics builds descriptions of motion, causality, energy, and the history of the cosmos. And then, when the clocks become accurate enough, they reveal that time is not the simple invisible river it first seemed to be. Before that surprise arrived, science needed a clean and powerful picture of reality. It needed a dependable stage on which objects could move, fall, orbit, collide, and obey mathematical laws. That stage was built with absolute space and absolute time, and for centuries it worked beautifully. Its greatest architect was Isaac Newton. Isaac Newton gave physics one of its most powerful clocks. It was not a clock made of brass, gears, springs, or a quietly judgmental ticking sound in the corner of a room. It was a deeper kind of clock built into the mathematical structure of nature itself. In 1687, Newton published his great work, The Mathematical Principles of Natural Philosophy, usually known simply as the Principia. In it he set out the laws of motion and universal gravitation, and gave the world a way to describe falling objects, orbiting planets, swinging pendulums, tides, projectiles, and machines with extraordinary accuracy. At the heart of that picture was a particular view of time. Newton thought of true mathematical time as something absolute. It flowed uniformly, in the same way everywhere, without depending on anything outside itself. Clocks might be imperfect, pendulums might slow, water clocks might drip unevenly. The rotation of Earth might not be a flawless timekeeper, but beneath all these practical instruments, Newton imagined a deeper time that passed steadily and equally, whether anyone measured it or not. This idea was not careless, it was enormously useful. To understand why, imagine trying to describe a ball rolling across a floor. You want to know where it starts, how fast it moves, how its speed changes, and where it will be after a certain amount of time. Newtonian mechanics gives you a clean framework for that. Position tells you where the ball is. Velocity tells you how its position changes with time. Acceleration tells you how its velocity changes with time. Force tells you what causes acceleration. The whole system works because time sits quietly in the background, steady and dependable, like a patient metronome that never gets tired and never asks for attention. In this view, different observers can disagree about many things. A person standing beside a road may say a carriage is moving quickly. A person sitting inside that carriage may say the carriage is at rest, and the road is moving backward. A sailor on a smooth ship may drop an object and see it fall straight down, while someone watching from shore may describe a curved path as the ship moves forward. These observers describe position and motion differently, but in Newton's physics they still share the same time. The seconds pass equally for all of them. That shared time made the universe mathematically manageable. Newton did not build this view from nowhere. Galileo Galilei had already helped prepare the ground by studying motion with unusual care. In the early 17th century, Galileo investigated falling bodies, rolling balls, pendulums, and the way objects continue moving when not strongly resisted. He challenged older Aristotelian ideas about motion and showed that motion could be studied through measurement, experiment, and mathematics. Time became something that could be counted, compared, and used to reveal patterns. A ball rolling down an inclined plane was not just an ordinary object moving on a slope. It was a way of slowing down falling motion enough to measure it. From Galileo to Newton, time became a mathematical tool of remarkable power. Newton's laws showed that the same principles could describe an apple falling near Earth, and the moon continually falling around Earth in its orbit. That was the great unification. The heavens and the ground were no longer separate realms obeying different rules. The same mechanics reached upward from everyday experience to the motion of planets. Time made this possible because it allowed change to be described precisely. Once you could say how position changed from one moment to another, and how velocity changed from one moment to another, motion became something physics could calculate. For ordinary life, this picture is still beautifully effective. If you throw a ball, build a bridge, design a clock, steer a ship, launch a modest rocket, or calculate the path of a planet moving far below the speed of light, Newton's physics often gives answers so good that the deeper theories are necessary. Engineers still use Newtonian mechanics constantly. Astronomers use Newton's laws as excellent approximations in many situations. Everyday machines do not usually need Einstein sitting quietly inside the gearbox, adjusting space-time with a tiny spanner. This is an important point. Newton's picture was not simply wrong, it was incomplete. It works because everyday speeds are small compared with the speed of light, and everyday gravitational fields are usually weak compared with those near neutron stars or black holes. In the world of thrown stones, walking people, swinging doors, falling rain, orbiting moons, and most human technology, absolute time is an extremely good approximation. It behaves so well that our intuition grows around it. We expect time to be shared. We expect two good clocks to agree. We expect the present moment here and the present moment far away to belong to the same universal now. But nature had hidden a problem inside light. In Newton's mechanics, speeds combine in a very ordinary way. If you walk forward on a moving ship, someone on shore adds your walking speed to the ship's speed. If a carriage rolls forward and a passenger throws a ball ahead, an observer on the ground describes the ball's speed as a combination of both motions. This feels natural. It matches ordinary experience. Light, however, would eventually refuse to behave quite so politely. By the 19th century, electricity and magnetism were being drawn together into a single theory. Experiments with electric currents, magnets, sparks, and fields showed that nature contained invisible structures more subtle than simple pushes and pulls. Michael Faraday pictured electric and magnetic fields spreading through space. James Clerk Maxwell later expressed these ideas mathematically and revealed that light itself is an electromagnetic wave. That discovery was magnificent, but it carried a quiet difficulty. Maxwell's theory pointed to a fixed speed for light in empty space, not a speed that simply belonged to a lamp, a star, or a moving observer, but a speed built into the laws of electromagnetism. If Newton's absolute time and ordinary speed addition were completely right, then measuring the speed of light should depend on how the observer moves. A person moving toward a beam of light should seem to meet it faster. A person moving away should seem to measure it slower. Yet the deeper story did not unfold that way. The old universal clock had worked almost perfectly for planets, machines, and falling bodies. But electricity, magnetism, and light were beginning to ask a more unsettling question. What if time was not the fixed background after all? What if the clock underneath the universe was not quite as absolute as Newton had imagined? The trouble began with light. For a long time, light had seemed strange but manageable. It travelled quickly, reflected from mirrors, bent through glass, spread into colours, and carried the image of the sun across empty space. Isaac Newton had studied light carefully, especially its colours, and had treated it partly as a stream of tiny particles. Others, including Christian Huygens, had argued that light behaved more like a wave. By the 19th century, that wave picture became much harder to ignore. The key figure was James Clerk Maxwell. Maxwell brought together the separate studies of electricity and magnetism into one unified theory of electromagnetism. Before him, Michael Faraday had imagined electric and magnetic fields filling space, curving around charges, wires, and magnets. Faraday's picture was physical and intuitive, but not written in the full mathematical form that later physics would need. Maxwell took those ideas and expressed them in a set of equations that described how electric fields and magnetic fields create and sustain one another. The result was one of the great surprises in science. Maxwell's theory showed that a changing electric field could create a magnetic field, and a changing magnetic field could create an electric field. Together, These fields could travel through empty space as a self-supporting wave. When Maxwell calculated the speed of this wave, it matched the known speed of light. Light then was not just brightness. It was an electromagnetic wave. That was a magnificent discovery, but it quietly disturbed the old Newtonian picture. In ordinary life, speeds add together. If a person walks forward on a moving ship, someone standing on the shore combines the speed of the person with the speed of the ship. If a carriage is moving and someone throws a ball from it, an observer on the ground measures the ball's motion as a combination of both movements. This is the ordinary, sensible, deeply unsurprising behaviour of speeds. It is also the kind of behaviour that lets the world get through the day without needing a philosophical crisis every time someone boards a train. But Maxwell's theory seemed to give light a definite speed in empty space. Not a speed that obviously belonged to the lamp, the star, or the observer, but a speed built into the structure of electromagnetism itself. Light in a vacuum travels at roughly 300,000 kilometers each second. The strange question was this: 300,000 kilometers each second relative to what? At the time, many physicists believed that waves needed a medium. Sound waves travel through air, water waves travel through water, and vibrations in a rope travel through the rope. So if light was a wave, it seemed natural to imagine that it also travelled through some hidden medium. This proposed medium was called the luminiferous ether. It was thought to fill space, carrying light waves across the universe, while somehow being almost impossible to feel, see, or disturb. The ether was a clever idea, but also a rather demanding one. It had to be stiff enough to carry extremely fast light waves, thin enough not to slow the planets, present everywhere, and yet strangely undetectable. As job descriptions go, this was ambitious. If the ether existed, Earth should be moving through it as our planet travelled around the Sun. That motion should have created an ether wind, a little like the apparent wind felt by someone cycling through still air. Light moving with this ether wind, and light moving across it should have travelled at slightly different measured speeds. The effect would be small, but with careful enough instruments it seemed measurable. In 1887, Albert A. Michelson and Edward W. Morley carried out their famous experiment in Cleveland, Ohio. They used an interferometer, an instrument designed to split a beam of light into two paths, send the beams in different directions, and then recombine them. If Earth were moving through the ether, the two beams should have taken slightly different times to complete their journeys. This would have shifted the pattern of light and dark interference fringes when the apparatus was turned, but the expected shift did not appear. The Michelson-Morley experiment failed to detect Earth's motion through the ether. It did not prove everything all at once, and science did not instantly wake up the next morning with special relativity neatly folded on the bedside table. But it created a serious problem. The ether had been introduced to make sense of light as a wave, yet one of the most careful experiments designed to detect it found no convincing sign of it. This was one of the first clear cracks in universal time. The problem was not just that one experiment gave an awkward result. The deeper issue was that Newtonian mechanics and Maxwell's electromagnetism did not fit together comfortably. Newton's world expected time to be shared and speeds to add in the ordinary way. Maxwell's world suggested that light had a special speed woven into the laws of electric and magnetic fields. Something had to give. Several important scientists tried to understand the puzzle before Einstein's final breakthrough. Hendrik Lorentz developed transformations that showed how measurements of length and time could change for moving systems in just the right way to preserve the speed of light. Henri Poincaré also recognized the deep importance of relativity principles and helped clarify the mathematical and conceptual structure around the problem. Their work prepared the ground for a new view of space and time. The important point is that time did not become questionable simply because philosophers sat around wondering whether clocks were suspicious. It became questionable because precise measurements, careful mathematics, and the behaviour of light forced the issue. Electromagnetism was not an abstract daydream. It described real fields, real waves, real circuits, real magnets, real light, and eventually the technologies that would reshape the modern world. The old picture had been wonderfully successful. Absolute time had guided falling bodies, projectiles, machines, moons, and planets. But light seemed to obey rules that were not comfortable inside that older framework. A solution was possible, but it required an extraordinary shift. Perhaps the speed of light did not need to be measured relative to an ether. Perhaps space and time were not fixed backgrounds after all. Perhaps observers moving differently through the universe did not merely disagree about position and speed, but about distance, duration, and even which events happened at the same time. That was the step Albert Einstein would take. Einstein's solution began with a strange act of trust. Instead of trying to rescue the old ether or force light back into the familiar habits of ordinary motion, he took the behavior of the light seriously. In 1905, Albert Einstein published his paper on special relativity. It did not begin by asking how the universe ought to behave according to common sense. It began with two principles that sounded simple but carried enormous consequences. The first principle was that the laws of physics are the same for all observers, moving at constant speed in a straight line. These observers are said to be in inertial reference frames. An inertial reference frame is a state of motion where, if no force acts on an object, that object continues moving steadily. A smooth train moving at constant speed, a spacecraft drifting through deep space, or a person standing still on a platform can each be treated as an inertial frame, as long as acceleration and gravity are not part of the immediate problem. The second principle was even more startling. The speed of light in a vacuum is the same for all inertial observers, no matter how the light source is moving, and no matter how the observer is moving. This was where ordinary intuition began to wobble slightly in its chair. In everyday life, speeds add together. If a person walks forward inside a moving train, someone outside the train combines the person's walking speed with the train's speed. But light does not follow that simple rule. A beam of light travelling through empty space is measured to move at the same speed by different inertial observers. Not almost the same speed, not the same speed after a polite adjustment, the same speed as a basic feature of nature. To make that possible, something else had to change. Einstein realized that measurements of space and time could not remain absolute. If everyone measures the same speed of light, then observers moving differently must sometimes disagree about distances, durations, and even whether two separated events happen at the same time. This is called the relativity of simultaneity, and it is one of the deepest ideas in special relativity. Imagine a long train moving smoothly past a station platform. A person stands at the exact middle of the train. Another person stands at the exact middle of the platform. Now imagine that two flashes of lightning strike the front and back of the train, leaving marks on both the train and the platform. The person on the platform might see the light from both lightning strikes arrive at the same moment. Since that person is halfway between the two strike marks on the platform, they conclude that the two lightning strikes happened simultaneously. In other words, from the platform's point of view, the front strike and the back strike occurred at the same time. But the person at the middle of the moving train is not in the same situation. As the light travels from both ends of the train passenger is moving toward the light from the front strike and away from the light from the back strike. Because the speed of light is the same in all directions for that passenger, the difference cannot be explained by one light beam travelling faster than the other. Instead, the passenger concludes that the front and back lightning strikes did not happen at the same time. Both observers are using the same laws of physics. Both are measuring light correctly. Neither one is confused, although this is a little unfair, because most of us feel at least mildly confused on their behalf. The shocking conclusion is that simultaneity is not universal. Two events that are separated in space can be simultaneous for one observer, and not simultaneous for another observer moving differently. There is no single cosmic present moment that stretches across the whole universe and tells every observer what is happening now everywhere else. The idea of one shared universal now belongs naturally to Newton's world, but not to Einstein's. This does not mean that time is fake. Special relativity does not say time is imaginary, meaningless, or merely a trick of the human mind. Clocks still tick. Events still happen. Causes still come before their effects when those events can physically influence one another. The important change is more precise than that. Time intervals depend on the motion of the observer measuring them. A duration that one observer measures between two events may not be the same duration measured by another observer moving differently. A length measured by one observer may not match the length measured by another. Space and time have not disappeared. They have become linked, flexible, and observer-dependent. This was a major break from Newton's absolute time. In Newton's physics, time flowed in the background with quiet independence. It did not care whether someone was standing on Earth, sailing across an ocean, riding in a carriage, or watching the planets. The same time passed for everyone. Space could be described differently by different observers, but time remained the shared foundation underneath it all. Einstein removed that foundation and replaced it with something stranger but more accurate. The laws of physics remained stable, but the measurements of space and time became relative to motion. What all observers could agree on was not a single universal clock, but the underlying structure of space-time and the fixed speed of light. This is why special relativity changed the meaning of time so profoundly. It did not merely add a small correction to Newton's theory. It changed the role time played in reality. Time was no longer an independent cosmic background against which everything moved. It was part of the physical relationship between observers, events, signals, and motion. And once simultaneity becomes relative, another consequence follows naturally. If observers moving differently cannot always agree on whether distant events happen at the same time, then moving clocks cannot be expected to agree perfectly either. A clock carried on a fast-moving train, spacecraft, or particle will not measure time in exactly the same way as a clock at rest relative to an observer. The disagreement is not due to a faulty mechanism. It is built into the geometry of nature. The end of one shared now leads directly to one of the most famous predictions in all of physics. Moving clocks run slow. Once the speed of light became fixed, time could no longer remain fixed in the old way. This is the heart of special relativistic time dilation. A clock moving relative to an observer is measured to tick more slowly than a clock at rest with that observer. That sentence can sound as if it belongs in the more suspicious corner of physics, but it is not a metaphor. It does not mean the clock merely looks slow because light takes time to travel. It means that when the two situations are compared properly, the moving clock records less elapsed time. One of the gentlest ways to see why this happens is through a thought experiment called a light clock. Imagine a very simple clock made from two mirrors, one above the other. A pulse of light bounces between them. Each bounce marks a tick. If the clock is sitting still beside you, the light travels straight up and down between the mirrors. The distance is simple, the path is short, and the tick is regular. Now imagine that same light clock moving past you very quickly, perhaps inside a smooth spacecraft. From the point of view of someone travelling with the clock, nothing unusual happens. The light still bounces straight up and down. The clock behaves normally. The traveller has no reason to look at their clock and say, "Well, that seems terribly relativistic today." But from your point of view, watching the spacecraft move past, the light does not travel only upward and downward. While the light moves between the mirrors, the whole clock also moves sideways, so the light follows a longer diagonal path. It has farther to travel between ticks. Here is the crucial point. The speed of light is the same for both observers. The light cannot simply speed up to cover the longer diagonal path in the same amount of time. So from your point of view, each tick of the moving light clock takes longer. The moving clock runs slow. That is time dilation. The traveller inside the spacecraft is not experiencing slow thoughts, slow heartbeats, or slow cups of tea. Everything inside their own frame of reference feels ordinary. Their clock, their breathing, their chemistry, and their nervous system all keep time together. Time dilation is not something a traveller feels locally. It appears when different observers, moving differently, compare their measurements. The size of the effect is described by something called the Lorentz factor. The Lorentz factor tells physicists how strongly special relativity changes measurements of time and length as speed increases. At everyday speeds, it is so close to ordinary Newtonian behaviour that nobody notices. A walking person, a moving car, or even a passenger jet experiences relativistic effects that are far too tiny for ordinary senses. But as an object moves closer and closer to the speed of light, the Lorentz factor grows. Time dilation becomes stronger, length contraction becomes stronger. The old Newtonian idea of one shared clock becomes less and less able to describe what is really happening. This is not just a clever idea built from imaginary mirror clocks. Nature actually does it. A famous example comes from muons. Muons are unstable particles, rather like heavier cousins of electrons. They are created when cosmic rays from space strike atoms high in Earth's atmosphere. On average, a muon at rest exists for only about 2.2 millionths of a second before it decays. Even travelling close to the speed of light, many muons should not survive long enough to reach the ground if time behaved in the simple Newtonian way, and yet many do reach the ground. From Earth's frame of reference, these fast-moving muons experience time dilation. Their internal clocks run slow compared with clocks on Earth, so their lifetimes are extended from our point of view. They travel much farther through the atmosphere than they otherwise could. Detectors at ground level measure them in numbers that make sense only when special relativity is included. The muons are not pretending. Tiny particles rarely have the theatrical range for that sort of thing. Their behaviour is a direct physical confirmation that moving clocks, even the natural clocks inside unstable particles, do not tick at the same rate as stationary clocks. Time dilation has also been tested with human-made clocks. In 1971, Joseph Haffel and Richard Keating flew highly accurate atomic clocks around the world on commercial aircraft. Some travelled eastward, some westward, and other clocks remained on the ground. When the flying clocks were compared with the ground-based clocks, they showed small differences in elapsed time, broadly matching the predictions of relativity when both motion and gravity were taken into account. The differences were tiny, measured on the scale of billionths of a second. But tiny does not mean unimportant. A billionth of a second is far beyond ordinary human perception, but atomic clocks are not relying on human perception. They count physical processes with extraordinary precision. When such clocks disagree in the way relativity predicts, the universe is giving a very quiet but very firm answer. Time dilation is real. It is not an optical illusion. It is not caused by faulty clocks. It is not simply that signals take time to reach someone's eyes. It is a measurable difference in elapsed time recorded by physical systems. Moving clocks genuinely accumulate less time along their paths than clocks that remain at rest in a given frame of reference. This changes the meaning of motion. In Newton's universe, motion changed where you were, but time flowed underneath everything in the same way. In Einstein's universe, motion also changes how much time passes for you compared with someone else. A journey through space is also, in a precise sense, a journey through time. For most ordinary journeys, the difference is almost unimaginably small. A trip to the shops will not leave one person dramatically younger than another, unless the queue is especially severe, and the emotional aging must be counted separately. But at speeds close to light, the effect becomes profound. A spacecraft travelling fast enough could cross enormous distances, while its passengers experience much less time than people waiting back on Earth. This leads to one of the most famous puzzles in relativity, the twin paradox. If one twin stays on Earth while the other travels through space at very high speed and later returns, the travelling twin can come back younger. The reason is not just speed, but the full path taken through space-time, including the acceleration needed to turn around and reunite. Once two travellers can meet again and compare clocks directly, the strange consequences of time dilation become unavoidable. Moving clocks run slow, and the universe keeps the receipts. The twin paradox is one of those ideas in relativity that sounds almost designed to cause trouble at the dinner table. Imagine two twins. One remains on Earth, the other boards a spacecraft, travels away at a speed close to the speed of light, turns around, and eventually comes home. When they meet again, they compare clocks, bodies, calendars, and probably a few awkward family stories. The twin who travelled through space has aged less than the twin who stayed on Earth. At first, this sounds like a contradiction. After all, special relativity says motion is relative. From the point of view of the twin on Earth, the spacecraft moved away and came back. But from the point of view of the travelling twin, Earth seemed to move away and later return. So why should one twin be younger than the other? Why does the universe choose sides? And why, after all this, is it apparently still not willing to help anyone look younger without a near light-speed spacecraft? The answer is that the two twins do not experience the same kind of journey. The twin who remains on Earth stays much closer to a single inertial reference frame. An inertial reference frame is a state of motion in which objects not acted on by forces continue moving steadily. In the simplified version of the twin paradox, Earth is treated as almost inertial, even though real Earth rotates, orbits the Sun, and is certainly not a perfect physics classroom. It is good enough for the basic idea. The travelling twin is different. To leave Earth, turn around and return, the spacecraft must accelerate. It must change speed, or direction, or both. That means the travelling twin changes reference frames. The two paths through space-time are not symmetrical. One twin remains mostly on one path. The other takes a very different path, involving high-speed motion and acceleration. This breaks the apparent paradox. The important point is not that acceleration itself magically causes all the aging difference. In many versions of the calculation, most of the difference comes from the long periods of high-speed travel. But acceleration is what allows the travelling twin to turn around, change frames, and return to the same place as the stay-at-home twin. Without that reunion, they could not stand together again and directly compare how much time each clock has recorded. This brings in a crucial idea called proper time. Proper time is the time measured by a clock travelling along its own path through space-time. Your wristwatch, your heartbeat, your chemical reactions, and the aging of your body all follow your proper time. It is the time experienced along your own route through the universe. You do not feel your own time slowing down. Locally, your seconds feel like seconds. Your tea cools normally. Your thoughts proceed normally. Your sandwich, regrettably, still becomes stale at the usual personal rate. But different paths through space-time can contain different amounts of proper time. That is the geometrical heart of the twin paradox. The twins do not merely move through space. They trace different paths through space-time. The stay-at-home twin traces one path. The travelling twin traces another. When those paths separate and later meet again, they can contain different amounts of elapsed time. A useful comparison is distance across a landscape. Two walkers can start at the same cottage and end at the same hilltop. One takes a fairly direct path, the other wanders through a valley, around a lake, up a ridge, back down again, and then eventually arrives at the same place, possibly with stronger opinions about footwear. They have shared the same start and finish, but they have not walked the same distance. In relativity, something similar happens with time, though the geometry is not the same as ordinary space. Two observers can begin together, separate and reunite. Their clocks then reveal how much proper time each path contained. The travelling twin's path through space-time can contain less elapsed time than the path of the twin who remained near Earth. This is not just a story about clocks being confused. A clock is a physical system. So is a human body. So is an unstable particle. If less proper time passes along one path, then every physical process following that path has less time in which to unfold. Fewer heartbeats occur, fewer chemical changes accumulate, less aging takes place. The travelling twin is not merely seen as younger. When the twins reunite, the travelling twin really has aged less. The deeper way to understand this came from Hermann Minkowski. In 1908, Minkowski presented a new interpretation of Einstein's special relativity. He argued that space and time should no longer be treated as separate backgrounds. Instead, they belonged together as space-time. Events were not just located by where they happened, but also by when they happened. The universe could be described as a four-dimensional structure, with time woven into the same mathematical fabric as space. Minkowski's famous insight gave special relativity a geometrical form. Motion was no longer just a change of position through time. It became a path through space-time. Time dilation was no longer an odd trick produced by fast motion. It became part of the geometry of those paths. This is why the twin paradox is so powerful. It takes the abstract idea of time dilation and makes it personal. It says that time is not simply a universal river carrying everyone forward at the same rate. It says that the amount of time you experience depends on your route through space-time. For everyday speeds, the difference is tiny. A person who takes a flight, rides a train, or walks briskly to the shops does not return dramatically younger than everyone else, though after a long enough queue, it may not feel that way. But at speeds close to light, the difference can become enormous. A journey that seems to last many years on Earth might last far less time for the traveller. The old picture of time as one shared cosmic ticking has now faded even further. Time is not just slowed by motion in a simple mechanical sense. It is measured along a path. It belongs to the shape of a journey through space-time, and that means time is no longer standing apart from the universe, flowing independently in the background. It has become part of the geometry itself. Once time becomes part of the path an object takes, the universe begins to look less like a stage with a clock hanging above it, and more like a structure made of events. An event in physics is simply something that happens at a particular place and a particular time. A flash of lightning, a heartbeat, a photon leaving a distant star, a cup touching a table, a signal arriving at an antenna, or a clock making one quiet tick can all be treated as events. Each one has a location in space, and each one has a moment in time. Neither part is enough by itself. Saying where something happened without saying when is incomplete. Saying when something happened without saying where is also incomplete, unless it was a very uneventful afternoon. This is the idea Hermann Minkowski placed at the centre of relativity in 1908. Space and time were no longer separate backgrounds. They formed a single, four-dimensional framework called space-time. In ordinary life, we describe position with three directions: left or right, forward or backward, up or down. Minkowski showed that time should be included with these, not because time is exactly the same as space, but because measurements of space and time are linked in special relativity. That distinction matters. Space-time is not simply ordinary space with a clock placed beside it. It is not a room with time painted on the wall as a helpful extra decoration. It is a unified structure in which different observers can slice space and time differently, while the deeper relationships between events remain consistent. One observer may measure a distance one way. Another observer, moving differently, may measure that distance another way. One observer may measure a certain amount of time between two events. Another may measure a different amount of time. Yet relativity is not chaos. It does not say everyone invents their own private universe. Instead, it says that although measurements of space and time can vary, there are deeper space-time quantities that all observers can agree on. One of the most important of these is called the space-time interval. The space-time interval is the combined separation between two events, taking account of both space and time. It is not exactly like an ordinary distance across a floor, because time enters the geometry differently from space. But its importance is similar. Different observers may disagree about how much of the separation belongs to space and how much belongs to time, but they agree on the space-time interval itself. This is called an invariant quantity. In physics, an invariant is something that stays the same, even when the point of view changes. In Newton's world, time itself was invariant. Everyone agreed on the same duration. In Einstein and Minkowski's world, that is no longer true. Observers may disagree about duration and distance separately, but they agree on the space-time interval between events. This is why space-time gives relativity its solid foundation. It lets the universe remain lawful even when space and time no longer behave like fixed universal measures. Space-time also tells us what can influence what. To see this, imagine a single event, a small flash of light in a dark room. From that event, light travels outward in every direction at the speed of light. After 1 second, the light has reached a sphere about 300,000 kilometers away. After 2 seconds, it has reached twice as far. If this expanding light is drawn in space-time, it forms what physicists call a light cone. A light cone shows the boundary of possible cause and effect. Events inside the future light cone can, in principle, be reached or influenced by something travelling from the original event at or below the speed of light. Events outside the light cone cannot be reached, because reaching them would require a signal faster than light. Events inside the past light cone are events that could have influenced the original event. This is one of the quietest but most profound roles of time in physics. Time is not merely a label we attach to change after the fact. It helps define causal structure. It helps say which events can be connected by signals, forces, messages, particles, and light, and which events are too far apart in space-time to have any direct influence on each other. Relativity does allow something surprising. For events that are far apart and not causally connected, different observers may disagree about which event happened first. One observer might say event A happened before event B. Another, moving differently, might say event B happened before event A. This sounds alarming at first, as if the universe has misplaced its filing cabinet. But causality remains protected. If one event can actually cause another, all observers agree on their order. A spark must happen before the fire it ignites. A signal must be sent before it is received. A falling glass must leave the hand before it hits the floor. No observer moving below the speed of light can reverse the order of cause and effect for events that are connected in this physical way. This is why the speed of light matters so deeply. It is not only the speed of light itself, it is the maximum speed at which information and influence can travel through space-time. It draws the boundary between the events that can be part of each other's story and the events that cannot yet know about each other at all. So time, in relativity, is not just a human convenience. It is not only what clocks show or what minds feel passing. It is part of the structure that separates possible causes from impossible ones. It helps shape the order of events, the limits of communication, and the geometry of every journey through the universe. Minkowski's space-time made special relativity clearer and deeper. It showed that the strange behaviour of moving clocks and relative simultaneity were not loose oddities scattered through physics. They were features of one underlying geometry. But Einstein was not finished. Special relativity dealt with observers moving steadily, without acceleration, and without gravity playing the central role. The next step was to ask what happens when gravity enters the story. If space and time are already linked, then perhaps gravity does not merely pull objects through space. Perhaps gravity changes the shape of space-time itself. Gravity does something quietly astonishing to time. In Newton's picture, gravity was a force acting across space. Earth pulled on the moon. The sun pulled on Earth. A falling apple was drawn downward by Earth's gravity, while Earth was drawn upward by the apple's gravity too, Although the apple's opinion on the matter was not especially noticeable, time still flowed in the background, steady and universal, while gravity moved objects through space. Einstein changed that picture again. In 1915, Albert Einstein completed the general theory of relativity. This theory did not describe gravity as an ordinary force pulling objects across an already fixed stage. Instead, it described gravity as the curvature of space-time caused by mass and energy. Matter and energy shape space-time, and the shape of space-time guides the motion of matter and energy. This is one of the great shifts in modern physics. A planet orbiting the Sun is not simply being tugged across empty space by an invisible rope. It is following a path through curved space-time. A falling object is not being pulled in quite the old Newtonian sense. It is moving along the natural path available to it in a space-time geometry shaped by Earth. And because space-time includes time, gravity does not only affect motion through space. Gravity affects the rate at which time passes. This effect is called gravitational time dilation. A clock deeper in a gravitational field ticks more slowly than a clock farther away from the source of gravity. Near Earth, this means a clock at sea level ticks very slightly more slowly than a clock on a mountain. A clock in orbit, farther from Earth's centre, and in a weaker part of Earth's gravitational field, ticks differently again. The effect is tiny in ordinary life. If you sleep downstairs and someone else sleeps upstairs, they are very slightly farther from Earth's centre, so their clock ticks a little faster than yours. This does not mean they are meaningfully racing into the future while you remain trapped in the living room. The difference is far too small for human senses, but with precise enough clocks it is real. The key idea is that gravity changes time itself, not merely the appearance of time. If two identical clocks are placed at different heights in a gravitational field, and then compared with enough precision, they will not record exactly the same elapsed time. The lower clock, deeper in the gravitational field, records less time. The higher clock records slightly more. Time does not pass at one identical rate everywhere. This may sound strange, but it follows naturally from general relativity. A gravitational field changes the geometry of space-time. Since clocks measure paths through space-time, their rates depend on where they are in that geometry. The closer a clock is to a massive body, the more strongly the curvature of space-time affects it. One important early test came from the Pound-Rebka experiment in 1959. Robert Pound and Glenn Rebka carried out the experiment at Harvard University. They measured the gravitational redshift of light in Earth's gravitational field using gamma rays travelling up and down a tower in the Jefferson Physical Laboratory. Gravitational redshift means that light changes frequency as it moves through a gravitational field. Light climbing upward away from Earth loses a little energy, and its frequency shifts downward. Light moving downward gains a little energy, and its frequency shifts upward. In the language of general relativity, this shift is closely linked to the fact that clocks at different heights tick at different rates. The height involved in the Pound-Rebka experiment was only about 22.5 meters. That is not a mountain. It is not a black hole. It is not even a particularly dramatic staircase. Yet the experiment measured a real effect predicted by general relativity. Earth's gravity was enough. Since then, gravitational time dilation has been tested with far greater precision. Modern atomic clocks are so sensitive that small height differences can be detected through changes in clock rate. Experiments using advanced optical atomic clocks have shown that even differences on the scale of centimeters can matter. A clock slightly higher in Earth's gravitational field ticks very slightly faster than one lower down. This is one of those facts that makes ordinary rooms feel quietly cosmic. The ceiling is aging a little faster than the floor. Not much, not enough to make the upstairs carpet wise and ancient, but enough that the principle is real. Gravity changes the passage of time everywhere gravity exists. That is important, because gravitational time dilation is often imagined only near black holes. Black holes are certainly the most dramatic examples. Near an event horizon, The difference between clocks close to the black hole and clocks far away can become extreme. But the effect is not exclusive to exotic objects. It exists around stars, planets, moons, buildings, mountains, and people. Every mass contributes to space-time curvature, although for small objects the effect is fantastically tiny. On Earth, the effect is mild but measurable. Near compact, massive objects such as neutron stars, it becomes far stronger. Near black holes, it becomes one of the defining features of the environment. But the principle is the same. Gravity and time are linked because gravity is the shape of space-time. This also means that any technology depending on precise time must take gravity seriously. Satellite navigation is the clearest everyday example. Satellites orbit high above Earth, carrying extremely accurate clocks. Those clocks are affected by two kinds of relativity at once. Their orbital motion produces special relativistic time dilation, making them tick slightly slower than clocks on Earth. But because they are higher up, in a weaker part of Earth's gravitational field, general relativity makes them tick faster than clocks on the ground. Both effects must be included. If they were ignored, satellite navigation systems would steadily drift out of accuracy. Positions calculated on Earth would become wrong by large distances. The calm little blue dot on a phone map depends in part on Einstein's description of time. So gravity changes time not as a poetic suggestion, but as a measured physical fact. Time runs differently at different heights. Clocks deeper in gravity tick more slowly. Clocks farther from mass tick faster. What began as a strange consequence of curved space-time has become part of precision measurement, laboratory physics, astronomy, and modern navigation. Time is no longer just flexible because of motion. It is flexible because of gravity too. One of the quietest ways relativity enters ordinary life is through a small glowing dot on a map. When a phone, car, aircraft, ship, or surveying instrument estimates its position, it often relies on signals from satellites high above Earth. The best-known system is the Global Positioning System, operated by the United States Space Force. Similar satellite navigation systems also exist around the world, including Europe's Galileo, Russia's GLONASS, and China's Beidou. Together, these systems form a kind of invisible timing web around the planet, constantly sending signals downward through space. The basic idea is beautifully simple. A satellite broadcasts a radio signal saying where it is and what time the signal was sent. A receiver on Earth picks up that signal and compares the sending time with the receiving time. Because radio signals travel at the speed of light, the receiver can work out how far away the satellite is from the time delay. Distance, in this case, comes from time. If a signal takes a tiny fraction of a second to arrive, that tiny delay corresponds to a large distance, because light travels so quickly. Light moves at roughly 300,000 kilometers each second in empty space. So an error of even a millionth of a second can mean an error of hundreds of meters. Satellite navigation is therefore not just about knowing where the satellites are. It is about knowing time with astonishing accuracy. This is why the clocks matter so much. Satellites in the Global Positioning System carry atomic clocks. These are not ordinary clocks with swinging pendulums or vibrating quartz crystals. They use the regular behavior of atoms to keep time. Atomic clocks are stable enough that small differences in timing, far below anything humans can sense, become measurable and useful. A person may not notice a few billionths of a second drifting past, but a navigation system certainly will. It is fussy in that way, though thankfully quite helpful about it. But the clocks in orbit do not tick at exactly the same rate as clocks on Earth. Two relativistic effects act on them at once. First, the satellites are moving quickly as they orbit Earth. Because of special relativity, a moving clock ticks slightly more slowly than a clock at rest, with the observer comparing it. From the point of view of clocks on the ground, the motion of the satellites slows the satellite clock a little. Second, the satellites are much higher above Earth's surface. They are in a weaker part of Earth's gravitational field than clocks on the ground. Because of general relativity, a clock farther from Earth's mass ticks slightly faster than a clock deeper in the gravitational field. So gravity makes the satellite clocks run faster overall. These two effects push in opposite directions. Motion slows the satellite clocks slightly. Weaker gravity speeds them up more strongly. The result is a net difference on the scale of about 38 microseconds per day, with the satellite clocks ticking faster overall compared with clocks on Earth. That may sound tiny. 38 microseconds is only 38 millionths of a second. It is not the sort of delay anyone would complain about while waiting for a kettle to boil, but for satellite navigation, it is enormous. If the relativistic correction were ignored, the system's position estimates would drift by kilometres in a day. A map that began by guiding you calmly down the right road would gradually become less confident, then less helpful, and eventually perhaps quite enthusiastic about sending you into a field. This is why relativity is not merely an elegant theory tucked away in a physics textbook. It is part of the machinery of modern life. The fact that time changes with motion and gravity is built into the calculations that allow aircraft to navigate, ships to cross oceans, tractors to guide precision farming equipment, emergency services to locate calls, and phones to show where we are. The same precision also matters beyond navigation. Financial markets use accurate timing to order transactions. Telecommunications networks rely on synchronized clocks. Scientific observatories compare signals across long distances. Power grids, data centers, and measurement laboratories all depend on careful timekeeping. Modern civilization is threaded together by time signals so precise that relativity can no longer be politely ignored. This brings us to the organizations that keep time itself carefully organized. The National Institute of Standards and Technology in the United States develops and maintains some of the world's most precise atomic clocks. Other national metrology institutes do similar work around the world. The International Bureau of Weights and Measures, based near Paris, helps coordinate global measurement standards, including international timekeeping. These institutions are part of the quiet scientific infrastructure that lets different countries, laboratories, satellites, computers, and instruments agree on what a second actually means, and the second is no longer defined by Earth's rotation alone. For most of human history, time was tied to the sky. A day came from Earth's rotation, a month came from the moon, a year came from Earth's orbit around the sun. Those cycles are still part of ordinary life, calendars, seasons, and sleep schedules. But Earth is not a perfect clock. Its rotation changes slightly because of tides, the motion of the atmosphere and oceans shifts inside the planet, and long-term gravitational interactions with the moon. Modern physics therefore defines the second using atomic behavior. More specifically, it is based on a particular transition in cesium-133 atoms. The idea is that atoms of the same kind behave identically anywhere in the universe, as far as physics can tell, making them far better timekeepers than a spinning planet with oceans sloshing around on it. This is a remarkable reversal. Humans first learned time from the sky, from shadows, sunrise, moon phases, and seasons. Now the most precise time comes from atoms, while satellites use that atomic time to guide people across Earth beneath them. The physics of time has moved from ancient sundials to orbiting clocks, from shadows on stone to radio signals crossing space. And in those signals, the deep lessons of relativity are quietly at work. Time is affected by speed. Time is affected by gravity. And if a civilization wants to know exactly where it is, it first has to understand how its clocks are moving through space-time. The second feels like one of the simplest things in the world. It is the small tick between one moment and the next, the little unit that lets minutes and hours build themselves into days. It is short enough to feel ordinary, but long enough that the mind can notice it passing. A second is a blink, a breath, a footstep, a quiet pause before answering a question, or the amount of time it takes to realize you have walked into a room and completely forgotten why you are there. But in modern physics, the second is not defined by a heartbeat, a pendulum, or even by the turning of Earth. It is defined by atoms. More specifically, the modern second is defined using Giesium-133 atoms. In the International System of Units, a second is based on a particular microwave transition between two energy levels in the ground state of a cesium-133 atom. The official definition counts 9,192,631,770 cycles of the radiation associated with that transition. That is not quite as cozy as saying 1 Mississippi, but it is considerably more reliable. The reason atoms are so useful is that atoms of the same kind behave in the same way. A cesium atom in one careful laboratory should have the same fundamental quantum properties as a cesium atom in another careful laboratory. Its energy levels are not decided by weather, politics, mood, or whether someone has had enough sleep. They come from the quantum structure of the atom itself. An atomic clock uses this regular quantum behavior as a timekeeper. Broadly speaking, the clock uses radiation tuned to a particular frequency, and it checks that frequency against the natural transition of atoms. If the radiation is slightly off, the clock can adjust it. The atom acts like a reference, a tiny quantum tuning fork, giving physicists an extraordinarily stable rhythm. This is very different from older timekeeping. For most of history, time was tied to Earth and sky. A day came from the rotation of Earth. A month came from the cycle of the moon. A year came from Earth's orbit around the sun. These are beautiful natural rhythms, and they still shape ordinary life. They decide calendars, seasons, dawns, evenings, and the small moral challenge of getting out of bed before sunrise. But Earth is not a perfect clock. The rotation of Earth changes slightly. The tides raised mainly by the moon and the sun slowly affect Earth's spin. The atmosphere moves, the oceans shift. Material inside Earth circulates and redistributes mass. Large earthquakes can make tiny changes to the planet's rotation. Over long periods, Earth's angular momentum changes, and the length of the day is not perfectly constant. This does not matter much for breakfast. It matters a great deal for precision science. If the second were defined only by Earth's rotation, then the unit of time itself would wobble slightly with the planet. That would be inconvenient for laboratories, satellites, communication networks, particle physics, astronomy, and any system that needs time to be stable at a very deep level. So modern science uses atomic time as the steadier foundation. This is where organisations such as the International Bureau of Weights and Measures become important. Based near Paris, it helps coordinate measurement standards used around the world. Timekeeping is not just a private matter for one clock in one laboratory. It is a global scientific agreement. National laboratories compare atomic clocks, contribute to international timescales, and help maintain a shared system that civil life, navigation, science, and technology can all use. Coordinated universal time is part of this practical system. It is the time standard used for clocks, communication, computing, navigation, and everyday civil time across the world. It sits at an interesting meeting point between atomic time and astronomical time, because human life still cares about the turning of Earth. Noon should not slowly drift into the middle of the night simply because atomic clocks are being admirably consistent. That is where leap seconds enter the story. Leap seconds have historically been added to keep coordinated universal time close to Earth's actual rotation. Because atomic time is extremely regular, and Earth's rotation is slightly irregular, the two can slowly drift apart. A leap second is a small correction, inserted when needed, to keep civil time aligned with the planet's orientation. The idea is simple enough, the practical details are less charming. Leap seconds can be awkward for computer systems, communication networks, financial systems, and any technology that prefers time to move forward in a perfectly predictable way. A clock that suddenly has an extra second can cause confusion. If systems are not designed to handle it properly, even time, it seems, occasionally has administrative paperwork. The search for better clocks has continued beyond cesium microwave clocks. Modern optical atomic clocks use transitions at much higher frequencies than microwave clocks. Higher frequency means many more oscillations in the same amount of time, which allows even finer measurement. Optical clocks can use atoms or ions such as strontium, ytterbium, aluminium, or mercury depending on the design. Some are so precise that if they could run perfectly for the age of the universe, they would lose or gain only a tiny fraction of a second. Their precision is so remarkable that they can reveal gravity itself. Because general relativity says clocks tick at different rates at different heights, an optical atomic clock can detect tiny changes in gravitational time dilation. Raise one precise clock slightly higher than another, and the higher clock ticks very slightly faster. In the best experiments, height differences on the scale of centimeters can become measurable through time. This is where the idea of perfect time becomes strangely slippery. The better clocks become, the less time looks like a single simple flow. Precision reveals the details. Earth rotates imperfectly. Gravity changes clock rates. Motion changes clock rates. Atoms provide stable rhythms, but those atoms still exist in physical places, moving through space-time, affected by their environment, their height, their speed, and the gravitational field around them. A perfect clock is not a clock outside the universe. It is a physical object inside the universe, and that means it belongs to physics. So the second, the most familiar small unit of time, turns out to rest on quantum mechanics, international measurement standards, atomic structure, Earth's imperfect rotation, and Einstein's relativity. The more accurately humans measure time, the more clearly time reveals its own nature. It is not just counted by clocks, it is shaped by the universe those clocks inhabit. Near a black hole, time becomes dramatically uneven. This doesn't happen because black holes are magical holes in space, or cosmic plug holes, or anything quite so theatrical. It happens because they are extreme predictions of general relativity. They are places where a huge amount of mass is compressed into a region so compact that spacetime becomes intensely curved. And when spacetime curves strongly, time is affected strongly too. In ordinary gravity, the effect is gentle. A clock on the floor ticks very slightly more slowly than a clock on a shelf. A clock on a mountain ticks very slightly faster than one at sea level. But near a compact, massive object, such as a neutron star or a black hole, the difference can become enormous. Gravity no longer gives time a tiny nudge. It begins to pull the shape of time into something much stranger. The first exact black hole solution came very soon after Einstein completed general relativity. In 1916, Carl Schwarzschild found a solution to Einstein's field equations, describing the space-time around a spherical, non-rotating mass. This solution revealed something extraordinary. If enough mass were compressed within a particular boundary, there would be a region from which not even light could escape. That boundary is called the event horizon. The event horizon is not a solid surface. It is not a shell, a wall, or a physical crust waiting in space. It is a boundary in space-time. Once something crosses it inward, all possible future paths lead deeper in. Escaping would require travelling faster than light, and relativity does not allow that. Light itself, the fastest signal in nature, cannot climb back out. This makes time near the event horizon especially strange when viewed from far away. Imagine a clock falling toward a black hole. To someone watching safely from a great distance, the falling clock appears to slow down as it approaches the event horizon. Its signals become more and more stretched out. Its light becomes more red-shifted, losing energy as it climbs away from the black hole's gravity. The distant observer sees the clock tick more slowly, and in the mathematical ideal, the clock seems to fade and freeze near the horizon. But that is not what the falling clock experiences. For an observer falling with the clock, local time feels normal. Their heart would beat normally. their watch would tick normally. If the black hole were large enough that tidal forces at the horizon were not immediately destructive, they could cross the event horizon without feeling a sudden bump or seeing a sign politely saying, "You are now entering a very poor life decision." This is an important distinction. From far away, the fall appears slowed and redshifted. From the falling observer's own point of view, their proper time continues forward. They do not see their own time stop. They cross the horizon in a finite amount of their own elapsed time, so it is not accurate to say that time simply stops for the person falling into a black hole. Time stopping is a description tied to what a distant observer calculates and sees through increasingly delayed and redshifted signals. The infalling observer's own experience is different. Relativity often works this way. It asks us to be careful about whose clock is being described. Black holes can also rotate, and real astrophysical black holes are expected to rotate because they form from spinning stars and grow by swallowing material with angular momentum. In 1963, Roy Kerr found a solution to Einstein's equations describing a rotating black hole. A Kerr black hole does not merely curve spacetime, it drags spacetime around with it. This effect is called frame dragging. Around a rotating black hole, spacetime itself is twisted by the black hole's spin. Objects near it can be pulled into motion around the black hole, not simply because they are orbiting in the ordinary way, but because the geometry of spacetime is being carried along. The region outside the event horizon where this dragging becomes unavoidable is called the ergosphere. It is one more reminder that general relativity does not treat space and time as passive scenery. They are active parts of the physics. For a long time, black holes were treated by some scientists as strange mathematical possibilities, rather than definite objects in the sky. That has changed. The Laser Interferometer Gravitational Wave Observatory detected gravitational waves from merging black holes in 2015. These ripples in spacetime matched the predictions of general relativity and showed black holes colliding far across the universe. The Event Horizon Telescope later produced images of the shadow regions around supermassive black holes, including the one in the galaxy Messier 87 and the one associated with Sagittarius A star at the centre of the Milky Way. These observations do not let anyone watch a clock hovering just above an event horizon with perfect clarity. But they do show that black holes are not just symbols in equations. They are real astrophysical objects, with masses, spins surrounding hot gas, gravitational waves, and observable effects on light and matter. Black holes reveal time at its most extreme. They show that time can stretch, slow, and differ radically between observers depending on gravity and motion. They make clear that time is not a universal background flowing evenly through all places. It is woven into space-time, and space-time can be bent into extraordinary shapes. But black holes are not the only places where time becomes profound. Extreme gravity shows how flexible time can be near compact objects. The universe as a whole raises a wider question. If space-time can bend, stretch, expand, and carry a history, then time itself may have a cosmic story. And that leads to one of the deepest questions in physics. When did cosmic time begin? Cosmology gives time a scale so large that ordinary clocks begin to feel very small. On Earth, we measure time with days, seasons, calendars, and atomic clocks. In relativity, we measure time along paths through space-time. Near black holes, those paths can become extreme and deeply curved. But when physicists look at the universe as a whole, they need another useful idea: cosmic time. Cosmic time is the time measured by observers who move with the average expansion of the universe. These are not observers flying rapidly through galaxies or falling toward black holes, but idealized observers carried along with the large-scale flow of cosmic expansion. If you imagine the universe on its broadest scale, with galaxies spread out like points in an expanding pattern, cosmic time is the clock that ticks for someone moving with that overall pattern. This does not mean every real object in the universe shares one simple local clock. planets orbit stars, stars orbit within galaxies, galaxies move within clusters, and gravity bends space-time in different places. But on the larger scales, when the universe is averaged out, cosmic time becomes extremely useful. It lets cosmologists speak meaningfully about the age of the universe, the formation of the first atoms, the birth of stars, and the long cooling history of cosmic expansion. According to the standard model of cosmology, the universe has evolved for roughly 13.8 billion years since its early hot dense state, commonly called the Big Bang. That phrase can be misleading. The Big Bang was not an explosion in the usual sense. It was not matter blasting outward into empty space from one central point, like a firework going off in a dark room. There was no outside room waiting patiently for the universe to arrive and make a mess of the furniture. The Big Bang theory describes the early expansion of space itself from a hotter, denser state. Space did not expand into something in the ordinary picture. The distances within space grew. The evidence for this view emerged slowly, through observation, mathematics, and a few moments where the universe seems to have leaned over and whispered, "Yes, this really is odd, but keep going." One of the central figures was Georges Lemaitre, a Belgian priest and physicist who proposed that the universe could be expanding. He connected Einstein's general relativity with the idea of a dynamic cosmos rather than a perfectly static one. Edwin Hubble then provided crucial observational evidence by studying galaxies and showing that distant galaxies generally appear to be moving away from us, with more distant galaxies receding faster. This relationship became known as Hubble's law. The expansion of galaxies does not mean Earth sits at the centre of the universe. Instead, it means space itself is expanding on large scales. Every distant galaxy can see other distant galaxies moving away in a similar broad pattern, just as points on the surface of an inflating balloon move farther apart without any one point on the surface being the centre of the surface. This expanding universe gives cosmic time a story. In the earlier stages, we can describe with some confidence. The universe was much hotter and denser than it is today. As space expanded, the universe cooled. Particles formed. Atomic nuclei formed. Later, electrons and nuclei combined into neutral atoms. Light that had previously scattered constantly through a hot plasma could then travel more freely. That ancient light still fills the universe today. It is called the cosmic microwave background. The cosmic microwave background is one of the most important pieces of evidence in modern cosmology. It is radiation left over from the early universe, stretched by cosmic expansion into microwave wavelengths. It comes from a time when the universe was only about 380,000 years old, which is ancient by human standards, but extremely young by cosmic standards. If the universe were a person 13.8 billion years old, which would be a difficult birthday party to arrange, the cosmic microwave background would be like a baby photograph from the first tiny fraction of its life. This radiation has been observed in extraordinary detail. The Cosmic Background Explorer satellite measured its spectrum and confirmed that it matched the expected thermal glow of the early universe with remarkable precision. The Wilkinson Microwave Anisotropy probe later mapped tiny temperature variations across the sky. The Planck spacecraft then measured those variations in even finer detail. These small patterns are important because they are the early fingerprints of the structures that later became galaxies and clusters of galaxies. So cosmic time is not just an empty counting system, it is tied to real physical stages in the universe's history. There was a time when the universe was too hot for atoms. There was a time when the first neutral atoms formed. There was a time before the first stars, sometimes called the cosmic dark ages. There was a time when the first stars and galaxies began to shine. Later still came heavier elements, planets, chemistry, life, and eventually creatures capable of worrying about whether they have left the oven on. The universe has a history, and cosmic time helps organize that history. But this naturally raises a difficult question. If the universe has an age, What happened before the Big Bang? This is one of those questions that sounds simple in ordinary language and becomes much more delicate in physics. In general relativity, space and time are part of the universe's structure. When we follow the expansion backward, the universe becomes hotter and denser, and eventually our current theories reach conditions where they are expected to break down. Near the earliest moments, gravity, quantum mechanics, and extreme energy scales all have to be considered together. The problem is that we do not yet have a complete, experimentally confirmed theory of quantum gravity. General relativity describes gravity and spacetime beautifully on large scales. Quantum mechanics describes matter and energy beautifully on small scales. But at the earliest moments of the universe, both are needed at once. Without a final theory combining them, science cannot simply state with certainty what happened at the very beginning, or whether before the Big Bang is even the right phrase. Some models suggest a beginning of time, some suggest a bounce from an earlier phase, some suggest more complex possibilities. But those ideas remain speculative unless they produce clear, testable evidence. The safest statement is more careful. Our observable universe has evolved from a hot, dense early state, and our current best-tested theories become incomplete as we approach the earliest conditions. Cosmology, therefore, gives time a grand history, but not a fully finished explanation. It shows that time can be discussed on the scale of the whole universe. It links the ticking of clocks to the cooling of space, the formation of atoms, the glow of ancient radiation, and the growth of cosmic structure. But it also brings back the deeper mystery of direction. The universe does not merely have time, it has a past that looks very different from its future. It began hotter, denser, smoother, and more ordered in certain crucial ways. Over cosmic time, stars formed, galaxies clustered, black holes grew, planets cooled, and complexity emerged. That difference between past and future is not explained by clocks alone. It belongs to the arrow of time. Time does not merely pass, it seems to point. This is one of the strangest facts hiding inside ordinary life. The past and the future do not feel interchangeable. Ice melts into water, but a puddle does not usually gather itself back into a neat ice cube. Coffee cools on a table, but a lukewarm cup does not suddenly steal warmth from the room and become hot again. Wood burns into ash and smoke, but ash and smoke do not casually reassemble themselves into a log. A body ages forward. A broken cup stays broken, unless someone repairs it, and even then the repair has its own history. This one-way direction is called the arrow of time. The arrow of time is not about clocks ticking. A clock can count seconds in either direction on a page if we choose to write the numbers that way. The arrow of time is about the physical difference between past and future. It is the reason some processes seem natural in one direction and absurd in the other. Smoke spreads through a room. Perfume diffuses into air. Heat flows from hotter objects to colder ones. Eggs scramble far more easily than they unscramble, which is unfortunate because breakfast would be much more forgiving otherwise. The key idea behind this arrow is entropy. Entropy is often described as disorder, and that is a useful first step, but it can also be misleading if taken too casually. In physics, entropy is connected to the number of microscopic arrangements that can produce the same large-scale state. A large-scale state is what we see from the outside: a gas filling a box, a cup of mixed coffee and milk, a shuffled deck of cards, or a warm room. The microscopic arrangements are the countless detailed positions and motions of the atoms and molecules making that state possible. A neat arrangement usually has fewer possible microscopic versions. A messy or mixed arrangement usually has many more. Imagine a deck of cards arranged perfectly by suit and number. There are very few arrangements that count as that exact ordered deck. Now imagine the same deck shuffled randomly. There are enormously many ways for the cards to be mixed. If the deck is shuffled again and again, it is overwhelmingly more likely to move from a special ordered arrangement into one of the many mixed arrangements than to accidentally return to perfect order. The same idea applies to physical systems. Gas molecules released in one corner of a room spread out because there are vastly more microscopic ways for them to be spread throughout the room than gathered neatly in one corner. Heat spreads because energy has many more ways to distribute itself among particles than to remain concentrated in one small place. A broken cup has many more possible scattered arrangements than the single very particular arrangement we call an intact cup. This does not mean that order can never increase locally. It can. A refrigerator can cool food. A living organism can build complex structures. A person can tidy a room, at least briefly, before entropy and laundry begin their quiet rebellion. But these local increases in order require energy and produce changes elsewhere. When the full system is considered, the broader tendency remains. This tendency is expressed in the second law of thermodynamics. In an isolated system, entropy tends to increase. The word tends is important. The second law is statistical. It is not saying that every tiny motion is individually commanded to become messier. It is saying that, for systems made of enormous numbers of particles, high entropy states are overwhelmingly more likely than low entropy states. The numbers involved are so vast that the direction appears practically certain. A room full of air could, in principle, have all its molecules randomly gather into one corner for a moment. But the probability is so fantastically small that waiting for it would be less a plan and more a lifestyle choice with no promising end date. The science of entropy was built by several major figures. Rudolf Clausius helped develop the concept in thermodynamics and gave entropy its name. Ludwig Boltzmann connected entropy to the microscopic behavior of atoms and molecules, showing how large-scale thermodynamic laws could arise from statistical mechanics. Josiah Willard Gibbs developed powerful mathematical tools for understanding ensembles of systems and helped deepen the statistical foundation of thermodynamics. Their work helped explain why the world has a direction even when many microscopic laws do not obviously contain one. This is the deeper puzzle. Many fundamental equations in physics work almost equally well if time is reversed. If you film two billiard balls colliding on a perfectly smooth table, the reversed film might still look physically possible. The basic laws describing the motion would not immediately object. At the level of individual particles, the past and future can be surprisingly symmetrical. But ordinary life is not made of two ideal billiard balls. It is made of huge numbers of particles interacting, spreading energy, mixing, scattering, radiating, colliding, and leaving records behind. A single molecule can move in a reversible way. A warm cup of coffee exchanging energy with a room involves unimaginable numbers of microscopic motions. The statistical pattern is what gives the process its arrow. This is why the arrow of time is not usually explained by microscopic laws alone. Those laws describe what individual particles may do. Entropy explains why large collections of particles almost always move from less likely large-scale states toward more likely large-scale states. Yet this answer leads to an even deeper question. If entropy tends to increase, why was entropy low enough in the past for it to increase from there? The arrow of time seems to depend on the universe beginning in a very special state. The early universe was hot, dense, and remarkably smooth. In some ways, smoothness sounds disordered, but when gravity is included, a smooth early universe actually represents a very special low entropy condition. Gravity tends to make matter clump into stars, galaxies, and black holes. A universe where matter was spread very evenly was not the most generic gravitational state it could have had. That low entropy beginning gave the universe room to evolve. Stars could form, heat could flow, structures could grow, records could be created. Memory, fossils, radiation, history, and aging all depend on this deep difference between past and future. So the arrow of time is not simply the ticking of a clock, it is the great statistical slope of the universe, running from a special low entropy past toward a higher entropy future. Time points forward, because the universe began in a state that allowed entropy to rise, and every cooling cup of tea is quietly following that cosmic direction. The past feels solid in a way the future does not. Yesterday seems to have a shape. It has already happened. It contains conversations that were spoken, meals that were eaten, light that entered eyes, messages that were sent, footsteps that crossed floors, and small decisions that cannot now be unchosen. The future, by contrast, feels open. It has possibilities rather than records. It feels like something not yet written, even though physics often suggests that nature is governed by laws rather than wishes. This difference is partly psychological, but it is not only psychological. The human experience of time is built from memory, attention, expectation, and consciousness. But those things are themselves physical processes. Memories are stored in brains through changes in living tissue. Written notes are ink or pixels arranged into patterns. Fossils are traces preserved in rock. Photographs are physical records of light. A message saved on a phone is information held in matter. Even the light from a distant star is a record of what that star was doing when the light began its journey. The past feels fixed because the past leaves records. A footprint in mud is a record of a foot pressing into soft ground. A fossil shell is a record of an organism that lived long ago. Tree rings record changing growth through seasons. Ice cores preserve tiny bubbles of ancient air. Light from the Andromeda Galaxy shows that galaxy as it was about 2.5 million years ago, because that light needed about 2.5 million years to reach Earth. The night sky is not simply a view of distant places, it is also a collection of distant times. Human memory works in the same broad direction, though in a much more complex biological way. The brain does not passively store perfect little films of the past. It changes through activity. Connections between neurons are strengthened or weakened. Patterns of activity become easier to recreate. Memory is active, living, and imperfect, which is why people can remember some things vividly, forget where they put their keys, and occasionally accuse the furniture of moving by itself. But even imperfect memory is still a physical record. Records form because physical processes leave traces, and those traces are linked to the arrow of time. When something happens, it can disturb the world around it. Light scatters, heat spreads, molecules move, surfaces are marked, signals travel, brains change, computers store bits. These processes are usually irreversible in practice because they involve many particles and increasing entropy. A cup breaking on a floor creates a record. Sound waves move through the air. Pieces scatter. Tiny fragments spread. The floor may be scratched. Someone nearby may form a memory of the event, especially if it was their favourite cup and they are now having a very small domestic tragedy. But the reverse process does not naturally happen. The sound does not gather itself back into silence. The fragments do not leap together. The scratch does not vanish, and the memory does not push the cup back into the hand. This is why the past has evidence and the future does not. Arthur Eddington helped popularize the phrase arrow of time in the 20th century. He used it to describe the one-way direction revealed by thermodynamics. The world contains processes that naturally point from past to future because entropy tends to increase. That same direction helps explain why records accumulate in one direction. Records are not floating outside physics. They are part of the same thermodynamic story. The future feels open partly because its detailed records do not yet exist. There is no fossil of tomorrow's conversation. There is no photograph already taken of the exact cup of tea you may or may not make next week. There is no memory of a decision that has not yet occurred. The future may be constrained by physics, biology, habit, weather, gravity, and whether the biscuit cupboard has already been emptied, but its fine details have not yet left traces in the world. This does not mean the future is completely free in a simple sense. Physics places strong limits on what can happen. A dropped object will fall under gravity unless something supports it. A hot cup will tend to cool in a cooler room. The moon will continue along an orbit governed very accurately by gravity. Many future events can be predicted with impressive precision. Eclipses can be calculated far in advance. Spacecraft can be guided across the solar system. Atomic clocks can count time with extraordinary stability. But prediction is not the same as total certainty. In classical physics, if someone knew the exact positions and motions of every particle and had unlimited calculating power, the future might seem fully determined. This was the dream often associated with Pierre-Simon Laplace, who imagined an intellect capable of knowing the past and future from the complete state of the universe. But the real universe makes this dream difficult in several ways. Chaos theory shows that some classical systems are extremely sensitive to initial conditions. A tiny difference in the starting state of a weather system can grow into a large difference later. The system still follows physical laws, but practical prediction becomes limited because no measurement is infinitely precise. Weather forecasting is not hard because clouds are being secretive for fun. It is hard because the atmosphere is a vast chaotic fluid system. Quantum mechanics adds another layer. In standard quantum theory, some measurement outcomes are described probabilistically, rather than as definite hidden details that were simply unknown beforehand. The theory gives extremely accurate probabilities, but not always a single predetermined result in the classical sense. Interpretations of quantum mechanics differ on what this means at the deepest level, but experimentally, quantum physics complicates the idea of a future that can be fully known in every detail. So the future feels open for several reasons at once. Its records do not yet exist. Many systems are too complex or chaotic to predict perfectly. Quantum events are described by probability, and conscious beings experience time from within, carrying memories in one direction while forming expectations in the other. Still, the difference between past and future is not merely a feeling. It is tied to causality, records, entropy, and the physical way information becomes imprinted on the world. The past feels fixed because it has left marks. The future feels open because those marks have not yet been made. And at the smallest scales where quantum mechanics becomes unavoidable, the question becomes stranger again. Time remains essential to the equations, but it does not always behave quite like the time of memory, cups, clocks, and broken things. At the smallest scales, time becomes both essential and strangely quiet. Quantum mechanics is the physics of atoms, electrons, photons, and the tiny systems that build the ordinary world. It began from a series of problems that classical physics could not solve. Max Planck introduced the idea of energy coming in discrete packets while studying the radiation from hot objects. Niels Bohr used quantum ideas to explain the structure of atoms. Werner Heisenberg developed matrix mechanics and the uncertainty principle. Erwin Schrödinger wrote a wave equation for quantum systems. Max Born gave the wave function its probabilistic meaning. Together, their work created a new picture of reality, one where particles could behave like waves, energy came in specific amounts, and measurement no longer meant simply revealing a perfectly definite pre-existing value. But time occupies an unusual place in this theory. In standard quantum mechanics, position can be represented by an operator. Momentum can be represented by an operator. Energy can be represented by an operator. These operators are mathematical tools connected to quantities that can be measured. Time, however, is usually treated differently. It often appears as an external parameter, the background variable according to which a quantum system changes. In simple terms, quantum mechanics often asks how the state of a system evolves as time passes, rather than treating time itself as something to be measured in exactly the same way as position or momentum. That may sound subtle, but it matters. In relativity, time is part of spacetime, affected by motion and gravity. In ordinary quantum mechanics, time often behaves more like the steady stage on which quantum states evolve. This difference is one reason the physics of time becomes so difficult when quantum theory and gravity are brought together. Still, quantum mechanics gives us the most precise clocks ever built. Atomic clocks work because atoms have stable quantum energy levels, an atom cannot have just any energy at all. Its electrons occupy allowed states, and transitions between those states involve very specific frequencies of radiation. In a cesium atomic clock, the second is defined by counting a precise number of cycles associated with a microwave transition, in cesium 133 atoms. The clock is not relying on a swinging pendulum, a turning planet, or the slightly optimistic rhythm of someone counting aloud. It is relying on quantum structure. Identical atoms have identical energy transitions as far as experiments can tell. That makes them wonderfully reliable timekeepers. So there is a strange balance here. Standard quantum mechanics treats time as an external parameter, but the best practical measurement of time depends on quantum systems. Time is not an operator in the usual basic formulation, yet atoms give us the clocks that define the second. Quantum physics also introduces a careful idea called the energy-time uncertainty relation. This idea is sometimes described too loosely, as if it means energy can simply be borrowed from nowhere for a short time, like the universe briefly misplacing its wallet. That is not the safest way to say it. The energy-time uncertainty relation is not exactly the same kind of statement as the position-momentum uncertainty principle. Position and momentum are both measurable quantities represented by operators in standard quantum mechanics. Time usually is not treated as an operator in the same way. The energy-time uncertainty relation is better understood as a family of related limits involving the duration of a process, the spread in energy, and how quickly a quantum state can change. For example, very short-lived unstable states tend to have less sharply defined energies. Processes that happen in extremely brief intervals can involve a wider range of energy values. The exact meaning depends on the context, so it needs careful handling. What matters here is that quantum physics links time to change at the deepest level. A quantum system evolves according to the Schrödinger equation. The wave function changes smoothly and predictably with time, at least when the system is not being measured. This smooth evolution can describe atoms, particles, fields, and delicate quantum states with extraordinary accuracy. Then measurement enters the picture, and things become less straightforward. In standard textbook quantum mechanics, measurement produces definite outcomes from a range of possible results. Before measurement, a system may be described by a superposition, meaning its wave function contains multiple possible measurement outcomes at once. After measurement, one outcome is found. This is not usually a problem for calculation, because the theory gives accurate probabilities, but it raises deep questions about what physically happens during measurement, and why the world we experience has definite records rather than visible superpositions of large objects. Time is involved in both sides of this puzzle. Quantum states evolve over time. Measurements happen at times. Records are formed in time. Yet the exact interpretation of measurement remains debated, with different views such as the Copenhagen interpretation, many worlds, Bohmian mechanics, and objective collapse theories offering different accounts of what the mathematics means. Another important concept is decoherence. Decoherence describes how a quantum system loses its delicate phase relationships when it becomes entangled with its surrounding environment. A tiny, isolated quantum system can preserve subtle timing and wave relationships. But a large warm object, constantly interacting with air molecules, light, heat, and internal vibrations, loses that delicate quantum behavior incredibly quickly. This is one reason tables, chairs, cats, and half-finished cups of tea do not usually behave like obvious quantum superpositions. Decoherence does not, by itself, solve every interpretation problem in quantum mechanics, but it explains why the classical world emerges so effectively from quantum ingredients. It shows how fragile quantum timing relationships can become hidden when systems interact with the wider environment. Modern particle physics goes further by using quantum field theory. In quantum field theory, particles are excitations of fields spread through spacetime. This framework combines quantum mechanics with special relativity, so time remains part of spacetime while quantum rules govern fields and particles. It is the language behind the standard model of particle physics, including electrons, photons, quarks, neutrinos, and the forces acting between them. Yet even this is not the final word. Quantum field theory works beautifully in flat spacetime or in situations where gravity can be treated separately. General relativity treats spacetime itself as dynamic and curved. Bringing quantum mechanics and curved spacetime together completely is the unfinished problem of quantum gravity. So at the smallest scales, time is not simply absent, nor is it fully understood. It guides quantum evolution, defines the rhythm of atomic clocks, enters uncertainty relations carefully, and sits inside the space-time structure used by modern particle physics. But when gravity and quantum theory meet, time becomes one of the deepest questions still waiting in the dark. The smallest known pieces of matter do not sit in empty space like tiny beads on a dark table. In modern physics, particles are understood in a deeper way. They are excitations of quantum fields, and those fields extend through space-time. This framework is called quantum field theory. A field is something that has a value throughout space and time. The electromagnetic field is a familiar example. It can carry light, radio waves, and the forces between charged particles. Quantum field theory takes this idea further. It says that what we call particles are not separate little objects placed on top of reality. They are local excitations or ripples of underlying fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Quarks, neutrinos, and other particles each belong to their own fields. This means that time in particle physics is not just a clock in the background. It is part of the space-time structure in which fields change, interact, and carry energy. Quantum field theory combines two great pillars of 20th century physics. From quantum mechanics, it takes the rules of probability, superposition, uncertainty, and quantist energy. From special relativity, it takes the fixed speed of light, space-time, and the requirement that causes cannot outrun light. The result is a theory where particles can be created and destroyed, where fields can fluctuate, and where interactions still have to respect the causal structure of space-time. This combination was not easy to build. Paul Dirac made one of the first great steps by creating a relativistic equation for the electron. His theory did something astonishing. It naturally pointed toward the existence of antimatter. The positron, the electron's antiparticle, was later discovered experimentally, confirming that this strange mathematical prediction had physical meaning. Later, quantum electrodynamics became the first truly successful quantum field theory of light and matter. It describes how electrons, positrons, and photons interact. Richard Feynman, Julian Schwinger, Shinichiro Tomonaga, and Freeman Dyson all played major roles in developing and clarifying it. The theory became famous for its extraordinary precision. In some measurements, especially involving the magnetic properties of the electron, its predictions match experiment to an almost absurd number of decimal places. Physics does occasionally show off. Feynman introduced a visual and mathematical tool called Feynman diagrams. These diagrams represent interactions between particles, such as electrons emitting or absorbing photons. They are not literal little cartoons of particles travelling through tiny pipes. They are calculation tools that help organise the possible ways fields can interact. This is especially important when discussing time. In popular explanations, antiparticles are sometimes described as particles moving backward in time. This idea comes from useful mathematical features in relativistic quantum theory, and from the way certain processes can be represented in Feynman diagrams. But it should not be taken too literally. A positron detected in a laboratory is not simply an electron actually travelling backward through time in the everyday sense. It is an antiparticle with measurable properties, moving forward through time like other physical objects we observe. The backward in time language can be helpful inside the mathematics, but if it is treated as a simple physical picture, it can mislead. Quantum field theory is subtle enough without giving particles tiny time machines and expecting them to behave responsibly. What matters more is that quantum field theory preserves causality. In relativity, two events are called space-like separated if they are so far apart in space and so close together in time that no signal travelling at or below the speed of light could connect them. One event cannot physically influence the other without faster-than-light communication. Quantum field theory respects this limit. Operations at space-like separated points cannot be used to send messages faster than light. This is crucial. Quantum physics contains strange correlations, especially in entanglement, but those correlations do not allow usable faster-than-light signaling. The causal structure of spacetime remains intact. Time still helps define which events can influence which other events. Modern particle physics is built on this framework. The Standard Model describes the known elementary particles and 3 of the 4 fundamental interactions: electromagnetism, the weak nuclear interaction, and the strong nuclear interaction. It includes electrons, quarks, neutrinos, photons, gluons, the W and Z bosons, and the Higgs boson. Gravity is not included in the Standard Model, which is one reason the search for deeper physics continues. Large laboratories test these ideas with extraordinary precision. The European Organisation for Nuclear Research, commonly known as CERN, operates the Large Hadron Collider near Geneva. In this enormous circular accelerator, particles are guided, timed, accelerated, and collided at extremely high energies. The timing has to be exquisitely controlled. Bunches of particles move around the ring at speeds extremely close to the speed of light, and detectors record the debris of collisions in tiny fractions of a second. So even in the most advanced particle experiments, time remains practical. It is not only an abstract coordinate in equations, it is part of how beams are synchronized, collisions are measured, unstable particles decay, signals are reconstructed, and discoveries are confirmed. Yet quantum field theory also brings us close to another deep question. At fundamental scales, many laws have important symmetries. Some processes can be described in ways that look almost unchanged when time is mathematically reversed. This is called time reversal symmetry. It does not mean ordinary broken cups leap back onto tables or smoke returns politely to a candle. It means that some basic physical equations retain their form when the direction of time is reversed. This creates a familiar tension. At the microscopic level, the laws can be highly symmetric. At the large-scale level, the universe has a clear arrow of time. Particles interact according to precise quantum fields in spacetime, while stars burn fuel, bodies age, heat spreads, and records accumulate. The deepest laws often look balanced, while the world we live in feels strongly one way. Quantum field theory therefore shows time in 2 forms at once. It is part of space-time, protecting causality and organizing interactions. It is also part of a deeper puzzle, because the fundamental rules can be far more time-symmetric than everyday experience suggests. The universe keeps its smallest clocks inside fields, particles, decays, and interactions. But the great arrow still points forward. Some physical laws seem to have a strange indifference to the direction of time. In ordinary life, this sounds completely wrong. A glass falls, breaks, and scatters across the floor. It does not gather itself back together, leap politely into the hand, and pretend nothing happened. Smoke spreads through a room. It does not drift backward into a candle flame. A warm object cools. A cold cup of tea does not become hot by stealing just the right amount of energy from the air around it, though many tired people would appreciate the feature. Yet at the level of basic equations, nature is often less committed to the obvious direction than everyday experience suggests. Time reversal symmetry is the idea that some physical laws still make sense if the direction of time is mathematically reversed. In a simple example, Imagine a small number of ideal particles moving and colliding without friction, heat loss, or outside disturbance. If their motions were reversed exactly, the same basic mechanical laws could describe the reversed motion. A film of two billiard balls colliding on a perfectly smooth table might still look physically possible if played backward. This does not mean that time really runs backward in the ordinary world. It means that many fundamental rules do not, by themselves, clearly mark one direction as the past and the other as the future. Classical mechanics often has this quality. Newton's laws can describe planets orbiting the Sun whether their motions are calculated forward or backward, as long as the positions and velocities are reversed appropriately. The mathematics does not immediately object. Quantum mechanics also has deep forms of reversibility in the smooth evolution of the wave function. When a quantum system evolves according to the Schrödinger equation, that evolution is highly structured and in many situations mathematically reversible. And this is exactly what makes the arrow of time so interesting. The large-scale world is full of irreversible processes. Ice melts, coffee cools, fuel burns, stars shine, bodies age, records form, entropy increases. But many of the microscopic laws underneath that world do not contain an obvious built-in arrow. The one-way flow of daily life therefore cannot be explained simply by saying that every basic equation has a little arrow stamped on it. Particle physics adds another layer to the story through symmetry. Three important symmetries are charge, parity, and time. Charge symmetry concerns what happens if particles are replaced by their antiparticles. Parity symmetry concerns what happens if a physical process is reflected in a mirror, with left and right reversed. Time symmetry concerns what happens if the direction of time is reversed in the mathematical description. For a while, physicists expected nature to respect some of these symmetries more completely than it actually does. The universe, as usual, had read the rules and decided to be more interesting. A major surprise came in 1956. Chien-Shiung Wu and her collaborators tested whether the weak nuclear interaction respected mirror symmetry. The experiment studied the beta decay of cobalt-60 nuclei at very low temperatures. If parity symmetry were always conserved, the process should have behaved the same way as its mirror image. But it did not. The weak interaction violated parity symmetry. This was a profound discovery. It showed that nature can distinguish left from right in certain particle processes. The mirror image of a physical process is not always an equally valid process. The result confirmed theoretical work by Zhongdao Li and Chen-Ning Yang, who had suggested that parity might not be conserved in weak interactions. So nature does not always respect mirror symmetry. Then came another surprise involving charge parity symmetry, which combines the replacement of particles with antiparticles and the mirror reversal of space. If charge symmetry and parity symmetry are applied together, some physicists hoped that the combined symmetry might still be preserved. But even this is not always true. In neutral kaons, charge parity violation was discovered in experiments associated with James Cronin and Val Fitch. Neutral kaons are particles containing quarks that can transform and decay in subtle ways. Their behavior revealed that the combined charge parity symmetry is not perfectly obeyed. Later, charge parity violation was also studied in beauty mesons, with theoretical understanding connected to the work of Makoto Kobayashi and Toshihide Masukawa. Their work helped explain how quark mixing could allow charge parity violation within the standard model of particle physics. These symmetry violations are real, measurable, and important. They help show that the microscopic world is not perfectly symmetric in every possible way. They are also connected to one of the great open questions in cosmology: why the observable universe contains far more matter than antimatter. Charge parity violation is likely part of that story, although the known amount in the standard model does not appear sufficient by itself to explain the full imbalance. But it is important not to blur this into a simple answer to the arrow of time. Known symmetry violations in particle physics do not by themselves explain why eggs scramble but do not unscramble, why smoke spreads, why bodies age, or why broken cups do not reassemble. Those everyday arrows are still overwhelmingly linked to entropy, statistical mechanics, and the low entropy condition of the early universe. There is a connection through deep symmetry principles. In modern physics, the combined transformation of charge, parity, and time has a special role in quantum field theory. Under broad assumptions, if charge and parity symmetry are violated, then time reversal symmetry is also involved in a subtle way so that the deeper combined symmetry remains preserved. But this is a statement about fundamental particle laws, not a direct replacement for thermodynamics. The two ideas must be held carefully together. At microscopic scales, many laws are nearly reversible, and some symmetries are exact or almost exact. Other symmetries, such as parity and charge parity, are known to be violated in specific interactions. At macroscopic scales, enormous numbers of particles interact, scatter, mix, and exchange energy. The statistical result is irreversibility. Entropy rises because high entropy arrangements are overwhelmingly more likely than low entropy arrangements. So the universe contains both symmetry and direction. Its deepest laws often look almost balanced between past and future. Yet the world built from those laws has a strong arrow, written in heat, memory, decay, records, and cosmic history. The laws almost run backward. The universe as a whole does not. The present feels like the most obvious part of time. The past is gone. The future has not arrived. The present seems to be the thin, bright edge where reality is actually happening. It is the moment in which a clock ticks, a thought appears, a breath is taken, a cup is lifted, and a person realizes they have once again paused a video to read something completely unrelated in the comments. But physics makes the present more difficult than it first appears. In everyday life, we imagine a shared now. There is now here, now across the street, now on the moon, now near the sun, and now in a distant galaxy. It feels natural to picture the entire universe as having one present moment spread across it, like a cosmic sheet passing steadily from past to future. That is very close to the Newtonian picture. In Newton's view, time flowed uniformly everywhere. Different observers could disagree about position and motion, but they still shared the same universal time. There was one great clock underneath reality, ticking equally for everyone. Special relativity changed that. Einstein showed that observers moving differently do not always agree about simultaneity. Two events that appear to happen at the same time for one observer may not happen at the same time for another observer moving at a different speed. This is not a problem with perception, nor a delay caused simply by light taking time to travel. It is built into the structure of spacetime. Imagine again the idea of distant lightning strikes or separated events in space. One observer may judge them simultaneous, after carefully accounting for light travel time. Another observer, moving relative to the first, may judge one event to have happened before the other. Both can be using correct measurements. Both can be obeying the same laws of physics. The disagreement is not about bad clocks. It is about the fact that simultaneity itself is relative. This means there is no single objective now spanning the entire universe, in the old Newtonian sense. There is no universal present moment that every observer, everywhere, must agree on. A local present still makes sense. The moment you are experiencing along your own path through space-time is real for you. Your clock ticks, your body ages, your thoughts unfold. Your surroundings have events that are close enough to be part of your immediate physical situation, but extending that local now across billions of light years is not something special relativity allows in a simple, observer-independent way. This is where the block universe idea enters the discussion. The block universe is one interpretation of relativity in which past, present, and future events are all represented within a four-dimensional space-time structure. Instead of imagining time as a flowing river carrying reality forward, the block universe imagines space-time more like a complete map of events. Each event has a place and a time within the structure. The birth of a star, the formation of a planet, a signal leaving a spacecraft, and a clock ticking in a quiet room are all located within spacetime. In this view, what we call the present is not a universal slice moving through the whole cosmos. It is more like the particular point, or local region, along an observer's path through spacetime. This idea can be powerful because it fits naturally with Minkowski spacetime. It respects the relativity of simultaneity. It explains why different observers can slice spacetime into space and time differently, while the deeper spacetime structure remains consistent. But it must be stated carefully. The block universe is an interpretation of what relativity suggests about spacetime. It is not a direct laboratory proof that human experience of the present is meaningless, fake, or worthless. Physics can say that there is no universal present shared by all observers in the Newtonian way. It does not thereby erase the reality of local experience, memory, causality, or proper time. Philosophers sometimes discuss this through ideas called presentism and eternalism. Presentism is the view that only the present is real. Eternalism is the view that past, present, and future events are all real in some sense within spacetime. Relativity creates serious challenges for simple presentism, because it becomes hard to define one universal present without choosing a preferred frame of reference. Eternalism often fits more comfortably with the spacetime picture, but the physics itself is more modest than the philosophy around it. What special relativity establishes is that simultaneity is relative. The speed of light is fixed for inertial observers, and measurements of time and space depend on motion. It does not settle every philosophical question about existence, experience, or becoming. The universe is under no obligation to make metaphysics convenient, which is inconsiderate but not especially surprising. Local time remains meaningful. Each observer follows a path through space-time, and along that path they measure proper time. That proper time is the time recorded by a clock travelling with them. It is the time of aging, breathing, thinking, moving, and changing. Even if there is no universal now spread across the cosmos, there is still a perfectly meaningful now, in the local sense of an observer's immediate experience. So does the present actually exist? In physics, the safest answer is that the local present exists as part of an observer's path through space-time. But a single universal present for the entire universe does not exist in the simple Newtonian way. The present is not a cosmic spotlight sweeping across all reality at once. It is local, relational, and tied to observers, clocks, signals, and causality. This weakens one of the most familiar ideas about time, but it does not destroy time itself. It shows that the present is stranger than intuition suggests. Relativity changes how time is organized, but it does not answer the deepest question of whether time is fundamental. That question reaches beyond special relativity, beyond ordinary clocks, and toward the unfinished search for a deeper theory of reality. There is a quiet question underneath all of this. Is time one of the basic ingredients of reality, or is it something that appears only when deeper physical relationships are viewed in the right way? At first, the answer seems obvious. Time feels fundamental, clocks tick, bodies age, light travels, stars burn. A cup of tea cools in a way that is both thermodynamically informative and personally disappointing. Everything we do seems to happen in time, so it is natural to imagine time as part of the deepest furniture of the universe. But modern physics makes the question much less simple. General relativity treats time as part of space-time. It is not a separate universal river flowing behind events. It is woven together with space into a dynamic structure that can curve, stretch, and respond to mass and energy. In general relativity, gravity is not simply a force moving objects through space. It is the geometry of space-time itself, and that geometry includes time. This means time is not just a passive background. It changes from place to place. It runs differently near Earth than it does high in orbit. It behaves differently near a black hole than it does far from one. It is shaped by gravity because it belongs to space-time, and space-time is shaped by mass and energy. Quantum mechanics, however, usually treats time in a different way. In standard quantum theory, the state of a system changes with time. Time is normally placed outside the system as the parameter that tells the wave function how to evolve. Position and momentum can be represented by quantum operators, but time usually is not treated in the same ordinary way. It sits in the background, more like the clock by which quantum change is described. So two of the most successful theories in physics treat time very differently. General relativity makes time part of a flexible, dynamical spacetime. Quantum mechanics usually treats time as an external parameter against which quantum systems evolve. That difference becomes a serious problem when physicists try to build a theory of quantum gravity. Quantum gravity is the unfinished attempt to reconcile general relativity with quantum mechanics. It is needed in places where space-time is extremely curved, and quantum effects are also important. The earliest moments of the universe, the deep interior of black holes, and the smallest possible scales of space-time all point toward this problem. General relativity works beautifully for planets, stars, galaxies, black holes, and the expansion of the universe. Quantum mechanics works beautifully for atoms, particles, fields, and radiation. But the deepest theory should somehow contain both. The difficulty is that gravity is not just another force in general relativity. Gravity is space-time geometry. If space-time itself becomes quantum, then time itself may also need to be reconsidered. This is where the problem of time appears. John Wheeler and Bryce DeWitt are closely connected with one of the most famous attempts to describe quantum gravity, through what is known as the Wheeler-DeWitt equation. In a simplified sense, this equation tries to apply quantum principles to the universe as a whole, but it raises a startling issue. Time does not appear in the expected ordinary way. That is deeply strange. A theory of the entire universe would seem to need time, because the universe clearly has a history. It expands, it cools, stars form, galaxies grow. People appear much later and begin wondering why time has become so difficult. Yet in some approaches to quantum gravity, time seems not to be fundamental in the familiar sense. This does not mean physics has proved that time is an illusion. That would be too strong. It means that, at the deepest theoretical level, time may not be the simple starting point we usually assume. Some physicists have explored the idea that time could be emergent. An emergent feature is something that appears at a larger scale from deeper ingredients. Temperature is a useful comparison. A single molecule does not have temperature in the same way a cup of water does. Temperature emerges from the average motion of many particles. It is real, measurable, and important. But it is not a basic property of one isolated particle. Time might be somewhat similar, though this remains an open question. Carlo Rovelli, one of the major figures associated with loop quantum gravity, has argued for approaches in which time is not an external clock standing outside the universe. In loop quantum gravity, space-time geometry itself is treated in quantum terms, and time may emerge from relationships between physical systems. The idea is not that nothing happens or that change is fake. Rather, the idea is that the familiar flow of time may arise from correlations, interactions, and thermodynamic behavior, rather than from one absolute universal clock. Other approaches also explore the possibility that space-time may be emergent. String theory is one major framework that tries to unify gravity with quantum mechanics by treating fundamental objects not as point particles, but as tiny extended strings. In some versions of string theory and related holographic ideas, space-time itself may arise from deeper quantum information or relationships. The holographic principle suggests, very broadly, that information describing a volume of space might be encoded on a boundary. Ideas like this have led physicists to ask whether space and time are built from something more basic. But this must be said carefully. String theory, loop quantum gravity, holography, and other approaches are serious areas of theoretical research, but none has yet become a confirmed final theory of quantum gravity. They contain powerful mathematics and suggestive ideas, but the experimental evidence needed to settle the question is not yet available. The deepest nature of time remains unresolved. The safest factual conclusion is that time is extremely real in measured physics, but not fully understood at the deepest level. Clocks measure it. Relativity shows it changes with motion and gravity. Quantum systems define it with extraordinary precision. Thermodynamics gives it an arrow. Cosmology gives it a history. Yet whether time is fundamental, or whether it emerges from a deeper structure, remains one of the great open questions. Physics has learned a remarkable amount about how time behaves. It has not yet fully answered what time is. After all of this, the most honest answer physics can give is both firm and careful. Time is real in the sense that physics can measure it, calculate with it, and observe its effects. Clocks record it. Equations use it. Signals depend on it. Causes and effects are ordered through it. Atoms, planets, satellites, particles, stars, and black holes all reveal something about how time behaves. It is not merely a feeling inside the human mind, even though the human experience of time is its own fascinating part of the story. But time is not real in the simple way it once seemed. Isaac Newton's absolute time was powerful, elegant, and deeply useful. In that picture, time flowed uniformly everywhere, independent of matter, motion, gravity, or observers. It was the same for everyone, like a cosmic clock ticking beneath the whole universe. That view still works extremely well as an approximation for everyday life. It is good enough for falling objects, machines, roads, buildings, and most ordinary speeds. If you are making toast, Newtonian time is usually sufficient, unless the toast burns, in which case time suddenly becomes a personal enemy. Modern physics shows that this old picture is incomplete. Special relativity says that time depends on motion. A clock moving relative to an observer is measured to tick more slowly than a clock at rest with that observer. This is not an illusion or a delay caused by light reaching the eye. It is a real difference in elapsed time. Fast-moving particles such as muons created in Earth's upper atmosphere survive long enough to reach the ground because their lifetimes are extended from Earth's frame of reference. Atomic clocks flown around the world have recorded tiny timing differences consistent with relativity. General relativity goes further. It says that gravity changes time too. A clock deeper in a gravitational field ticks more slowly than a clock farther away. A clock at sea level ticks very slightly more slowly than a clock on a mountain. A clock in orbit ticks differently from a clock on Earth's surface. These differences are small near Earth, but they are measurable, and they matter. Satellite navigation depends on correcting for both motion and gravity. Without those corrections, positions on Earth would drift badly out of accuracy. So time exists physically, but it is flexible. It is not one universal flow shared identically by every observer everywhere. It is local. It is measured along paths through space-time. It depends on motion. It depends on gravity. It helps define which events can influence which other events, because no signal can travel faster than light. In relativity, time is not just a background for events. It is part of the structure that connects events. Then there is the arrow of time. The equations of physics often work surprisingly well in both time directions, especially at microscopic scales. But ordinary life does not. Heat spreads, smoke disperses, bodies age, records form, cups break more easily than they reassemble. The direction from past to future is strongly linked to entropy and to the second law of thermodynamics. In an isolated system, entropy tends to increase. This statistical tendency gives ordinary physical processes their direction. Yet the deepest origin of that arrow is still not fully settled. The universe seems to have begun in a very special low entropy state. That early condition allowed entropy to rise, stars to form, heat to flow, records to accumulate, and history to unfold. Why the early universe had that special condition remains an active question in cosmology, and fundamental physics. Black holes deepen the picture by showing time under extreme gravity. Cosmic expansion gives time a large-scale history. Quantum mechanics complicates time by treating it differently from position and momentum in standard theory. Quantum field theory uses time within spacetime while preserving causality. Quantum gravity then raises the most difficult question of all, whether time is truly fundamental or whether it emerges from something deeper. This is where established physics and open theory must be kept separate. It is established that time dilation from motion is real. It is established that gravitational time dilation is real. It is established that atomic clocks confirm tiny differences in elapsed time. It is established that modern navigation and precision measurement depend on these effects. It is well supported that the thermodynamic arrow of time is tied to entropy and the low entropy past. But it is not established that time is emergent. It is not established which theory of quantum gravity is correct. It is not established what happened at the very earliest moment of the universe, or whether asking what happened before the Big Bang is always meaningful. These are serious scientific questions, but they remain unresolved. So the final picture is calm, strange, and factual. Time is real, measurable, flexible, local, and deeply woven into physical law. It is not the simple cosmic ticking that ordinary intuition first imagines. It is shaped by speed, gravity, entropy, quantum behavior, and the structure of spacetime itself. The clock was never simple. It only sounded that way because it was ticking quietly. The physics of time reveals a clock that was never simple. Time is measurable and real, but it is not universal in the old comfortable sense. It is not one invisible substance flowing identically through every place, every observer, and every corner of the cosmos. Clocks measure real physical processes, but those processes are shaped by motion, gravity, quantum behavior, and the structure of space-time itself. The journey began with ordinary timekeeping with shadows, water clocks, pendulums, planetary cycles, and the ancient human habit of reading time from the sky. Then came Newton's absolute time, flowing evenly beneath falling apples, orbiting moons, and the clean mathematics of motion. That picture was powerful, and for everyday life it remains wonderfully useful. But light opened the first crack. Maxwell's electromagnetism suggested that light had a definite speed built into nature. The Michelson-Morley experiment failed to find Earth's motion through the luminiferous ether. Then Einstein's special relativity showed that space and time must change together if the speed of light is the same for all observers moving steadily. From there, the simple clock disappeared. Simultaneity became relative. Moving clocks were shown to tick slowly. The twin paradox revealed that different paths through space-time can contain different amounts of aging. Minkowski's spacetime turned time into part of a four-dimensional structure of events. General relativity then made spacetime dynamic, so gravity could change the rate at which clocks tick. That is not just theory. Particles moving near the speed of light age differently. Atomic clocks confirm tiny timing differences. The global positioning system depends on relativistic corrections, or navigation would drift badly out of accuracy. Black holes show time at its most extreme. Cosmic time gives the universe a large-scale history. Entropy gives that history a direction, linking the arrow of time to the low-entropy early universe. Quantum mechanics, quantum fields, symmetry, and the question of the present all deepen the mystery. And quantum gravity leaves the hardest question still open, whether time is fundamental, or whether it emerges from something deeper. So time is not merely a human illusion, but it is also not the simple, universal ticking clock humans first imagined. It may be the most familiar part of life and one of the least intuitive parts of physics, quietly shaping every event while refusing to behave like something simple.